Did the guy rip me off? Is it really made out of gold? And he tried to figure out how do I do that, right? And he said, oh, if you weigh it in the water, the display, you can tell, right, by the density change. And his principle became, and his idea was that the buoyant force of a fluid, is equal to the weight of the fluid displaced by the object. Displaced by the object. So, when you can remember those words and remember that idea, it makes this make a lot more sense, because we could do a whole pressure derivation and the subtracting of the volumes and the area and the density and the, oh, that works out to this exactly. So, one of the rare times I think memorizing the summary of it is better than proving it the long way. That idea that pressure is deeper on the, more on the bottom, less on the top. So yes, there's this difference in pressure based on how much mass, the weight that we took out of there, right? There's going to be the difference in pressure. So I want to make sure we can calculate that. So as a formula, buoyancy is a force, so buoyant force equals the weight of the fluid displaced by the object. So how do we get, so that's going to be mg, right? Mass displaced. All right, how can I calculate the mass of an object if I don't have that weight? Maybe I know something else. Oh yeah, mass is going to be density times volume. All right, leave room for subscripts because I want to make the subscripts make sense. If it's the mass of the fluid displaced, which density are we using? Density of the fluid, right? Could be water, could be something else. Like for a helium balloon, that fluid is air, right? It's going to float. Oh, a buoyant force, right? And this volume will be the volume of the object. Nice. Does that make sense? So, really gotta, I know subscripts, we go crazy with them. I kind of tend to write them out. You could do F and obj. I think an O is a little bit confusing. It's not the original volume, it's the, right? So be very, very careful. Boy. Yeah, boy.
Boy.
All right.
What is that?
So you're going to float or not?
He's recording this.
Yeah, see, everybody's going to know what I have to put up with during class, huh?
What? No, you said it.
So how do you know if it floats or not?
You need to know something. Or the mass before it would sing, or the weight before it would need to sing.
All right. Sinks. Floats. And yes, it is this easy when you think about it. It sinks if the weight of the object is more than the buoyant force. So when does it float?
When it's less?
less than,
What if it's equal to?
less than,
So, hold on. So, that depends which way you phrase it, right? So, when the buoyant force is more than the weight of the object.
Wait, then how does ships build?
How are ships built? So that the buoyant force is more than the weight of the ship.
But
Where's the
ship's way more. Oh, is it the volume?
value?
Oh, right. What do you mean the ships weigh more than the fluid they displace? That would mean they sink. Wait, big ships are made out of steel, and that's heavy, right?
even the ocean.
Are they solid steel?
No, it's hollow.
No, they're hollow, right? They build the outside, and then they have this big airspace inside, right?
Bless.
So, ooh, how does this work with densities too, right? We want to compare densities when they sink or float. So on average, we need that shape, right? That shape to displace more than the weight of the steel that's made to make the outside, right? That the steel plus air weight averaged over the volume, all that has to weigh less than the amount of water it pushes out of the way. So it's pushing out of the way a volume, and it is a volume. What does that say about the densities? Weight of the object is more than the buoyant force. So the weight is mg, right?
Yeah.
Mg is greater than the buoyant force. Mass of what? Object, right? How do you figure out the mass of the object? You weigh it, or
PV.
PV.
rho v, right? So rho vg, I'm sorry, in this case it's greater than, right? Sorry. Density of what? The object. Volume of the object. G of gravity. Yeah, that's for both, right? Is greater than, what's the buoyant force again?
PVG.
Rho. We gotta say rho because P's pressure. So it's a rho vg. Wait, rho vg greater than rho vg?
Different.
Oh,
rules.
subscripts matter, right?
So
Oh.
All the G's cancel.
when the density
We
of
can
the
just
object
compare
is
densities, right? When the density of the object is greater than the density of the fluid, it sinks. Wait, steel! Steel is way more dense than water for those big ships.
But the actual.
Oh, the average density, right, of the entire volume of the ship. Does that make sense? So when you take the steel and all the airspace inside, that average density is less than water. Cool.
Is there a way an object can only sink to a certain distance, like depth?
Like it sinks and then now it doesn't sink anymore?
Yeah, and it evens out.
Will sink.
Let's talk about it. In
You float.
in air, you can kind of have that like altitude where you kind of float up to and won't float any higher. Well, is that right? That kind of goes the opposite direction. Yeah, because the density gets slighter. Yeah, you would get that height that you would float up to. In water, liquids are very incompressible, right? So when we talk about fluids, yes, liquids and gases are both fluids. The big difference is you can compress a gas, right? We got our piston cylinder is, yeah, we compressed that gas and got it real hot. If we fill this with water and then put the piston, you can't really squish a liquid. Liquids don't squish hardly at all. So liquids are incompressible fluids where gases are compressible fluids. So when you get the higher level like aerodynamics, hydrodynamics, there's a difference because of the compressibility of gases.